The three main forces that are causing fluid movement at the glomerulus are the hydrostatic pressure, which is essentially the blood pressure, the colloid osmotic pressure from the proteins that are in the plasma, and the fluid pressure created by the fluid in Bowman's capsule. So let's put some numbers on this here. So the hydrostatic pressure, essentially the blood pressure, that's pH, and it's listed here as 55 millimeters of the mercury. From that we need, and that's an outward force, a very strong outward force. So it's pushing fluids out of the capillaries here into Bowman's capsule. Then we have an inward force that puts the fluids back in here, and that would be the colloid osmotic pressure caused by the plasma proteins that are in the blood. And that's here minus 30 millimeters of the mercury. And then we have another inward driving force, and that would be the fluid pressure created by the fluid in Bowman's capsule. As fluid builds up here, we're pushing fluids back into the blood, and that's minus 15 millimeters of the mercury. When it's all said and done, we have 55 minus 30 minus 15, which adds up to 10 millimeters of the mercury, and that is your net filtration pressure of 10 millimeters of the mercury. And those are the fluids that end up then going into the tubular network of the nephron. Together with your 2 million nephrons per day, this adds up to a filtration of 180 liters per day. And that is a huge amount of fluid. So now let's take a look at the glomerular filtration rate. That means the per minute volume of fluids that are being filtered at the level of the glomerulus. There are two main factors, and they are the net filtration pressure, which is the hydrostatic pressure minus the colloid osmotic pressure minus the fluid pressure, which we just looked at. So the 10 millimeters of the mercury. And then we have a filtration coefficient that's dependent on the surface area of the glomerular capillaries, available filtration, and the permeability of the interface between the capillary and Bowman's capsule. So now, when you are calculating all of this, you would be calculating this glomerular filtration rate, and what you would find is that even in a very large range of blood pressures, where between 80 and 180 millimeters of the mercury, and keep in mind, normal mean arterial pressure is right around 100, so 93 to be exact would be normal mean arterial pressure. Anywhere between 80 millimeters of the mercury and 180, we are keeping the glomerular filtration rate constant. That means there are regulatory processes at work that will adjust for blood pressure, for the changes in blood pressure, and keep the glomerular filtration rate constant. One of the factors that help to keep the glomerular filtration rate constant over a wide range of mean arterial pressures is the ability to change the resistance in the renal arterioles. So right here we have the afferent arteriole going into a glomerulus, and we can adjust the width of this blood vessel right here. And so as we can adjust the resistance to flow, that means we can adjust the glomerular filtration rate. Let's say that blood pressure is actually really high, then we would end up increasing the glomerular filtration rate because our filtration pressure increases. So now we can narrow down this vessel and sort of regulate the amount of blood that ends up going into the glomerulus and at much pressure it goes into the glomerulus, so that we keep our GFR, the glomerular filtration rate, constant. So here's the example of vasoconstriction. We're just going to narrow down this vessel. Less blood comes through. Let's say blood pressure is really high here. We just kind of shut down this vessel just a little bit and adjust for the flow into the glomerulus. Other factors that help regulate the glomerular filtration rate are listed here. We have a myogenic response. Myo refers to muscle, so that is the intrinsic ability of vascular smooth muscle to respond to pressure changes, and that's similar to autoregulation and other systemic arterioles. Then we also have tubuloglomerular feedback, that's via paracrine control, and then hormones and autonomic neurons that can change the resistance in arterioles and alter the filtration coefficient. This diagram here shows how the macula densa cells help to regulate the glomerular filtration rate, the GFR. So we're going to focus here on this box that's enlarged over here. And important here are these macula densa cells. And you can see here the afferent arteriole coming in here, the efferent arteriole, and then here will be the ascending limb of Henle's loop coming by. And there are these macula densa cells that measure pressure, actually, and they can release paracrines that affect the arteriole diameter. So basically, we have this measurement mechanism that then gives feedback and is able to release local hormones for paracrine control. And here is a flow chart that explains sort of step by step how the macula densa cells are able to regulate glomerular filtration rate. So let's say the GFR increases. Let's say somebody has ultra high blood pressure, and now the GFR is bound to increase. We want to counteract that because we like to keep our GFR constant. So as the GFR increases, the flow through the tubule increases, and that means that the macula densa cell, the flow through these macula densa cell increases. And now we're going to send out paracrine signals that counteract that, and we will constrict the afferent arteriole and therefore affect the resistance in these arterioles, and therefore then the hydrostatic pressure in the glomerulus decreases and the GFR decreases to where we would want it to be. Now let's move on from filtration to reabsorption. So collectively, your 2 million nephrons or so, the glomeruli, they will filter about 180 liters of fluid per day. 180 liters per day. And there's no way you would lose that much fluid and survive. So we need to reabsorb the vast majority of that. This here's filtration. Now we need to move on to reabsorption. Let me put it down here. Reabsorption. So we need to reabsorb 178.5 liters per day out of those filtered 180 liters per day. The question is, how do you do that? And so we have these 180 liters now in these renal tubules, and we need to gain the vast majority of the water and the electrolytes and nutrients. We need to gain all of that back. So here, this diagram shows you how some of the items are regained or reabsorbed. Sodium reabsorption is typically active transport. So here we have active transport, sodium active transport. Then anions, we usually employ a electrochemical gradient that drives anion reabsorption, so that takes care of the anions, negatively charged particles. Water reabsorption, a lot of the water follows the salt, so by osmosis. So as you are reabsorbing salts, then the water moves by osmosis, and the concentration of other solutes increases as the fluid volume in the lumen decreases, and so basically the water follows the salt. And here we have potassium, calcium, and urea. The permeability of these solutes depends on where you are in the tubular network, and you have a variety of transporters, or you also have paracellular pathways where you're going between cells, for example. So if you think about it, it's a huge task. So you need to reabsorb a lot of water, most of your electrolytes, and then you want to keep the calcium, of course. Some waste products, of course, need to be excreted. And the kidneys are workhorses. They're working 24/7, tirelessly filtering and reabsorbing all day long. So in general, there are two ways substances can be reabsorbed from the tubular lumen of the renal tubules back into the blood. You can go through the cells. There will be transcellular transport or transepithelial transport, since we have a single layer of epithelium that makes up these renal tubules. So that means we need to get the substance across the apical and the basolateral membranes of the tubular epithelial cells. Or you can go between the cells. There'll be the paracellular pathway where the substances need to pass through the cell-cell junctions between two adjacent cells. Here you have an example of transepithelial transport where we're basically driving the sodium transport by active transport, so under expenditure of ATP on the basolateral side. So here's the renal tubular lumen, here's the interstitial fluid, and then over here would be the blood. So this will be into the blood. So we're driving everything here on the basolateral side by using a sodium potassium ATPase in this case. And as the sodium is being pumped out, it creates a low concentration gradient inside of the cell right here, which then drives the downhill concentration gradient of sodium ions into this epithelial cell. So basically you're driving everything with spending some ATP right over here with an ATPase pumping one substance, and then you're generating a concentration gradient that drives the movement of sodium ions, in this case by a concentration gradient. So this doesn't cost you any energy over here. Here's another example of transepithelial transport. This is how glucose and also other substances get across the epithelium from the tubular lumen back into the blood. And so basically think of it this way. Here this ATPase drives the pumping of sodium. Also in exchange for the sodium out, you get potassium in, so it's an exchange right here. But basically that pumping of sodium outside of the cell makes the concentration inside of the cell very low, of sodium that is. And now the sodium has a concentration gradient because it's in high concentration in the lumen of the kidney tubules, the renal tubules, and now it's going down a concentration gradient into this epithelial cell. As sodium is going down a concentration gradient, it gives glucose a free ride. So we have a sodium glucose co-transporter here where they both go in the same direction. And then the glucose goes out the cell and gets back into the blood through this glucose transporter molecule. And then here again, this is the whole driving force. So really the expenditure of ATP here, pumping the sodium out and getting an exchange here for the potassium, it has multiple effects. It creates this downhill concentration gradient for sodium that allows sodium to move into this epithelial cell and then eventually out, of course. And it also gives the glucose a free ride into the cell and eventually out of the epithelial cell back into the blood. This is how glucose gets reabsorbed, and also other nutrient molecules such as amino acids and organic metabolites. Now let's take a look at the salt and water reabsorption in proximal convoluted tubule. So here's a nice big bold picture of Bowman's capsule and sort of glomerulus right here. So we're going in here through the afferent arteriole. Here's a capillary bed. Your collective 180 liters per day are being filtered out here. And what comes out here is the efferent arteriole. You can see the vessel is considerably smaller because you've lost so much fluid. So what comes out here is much more concentrated and has lost a lot of fluids. So collectively here we have 180 liters per day that are filtered out in the glomerulus. And now the big job of reabsorption has to start. Reabsorption hinges on the active transport of sodium. So here's our active transport of sodium. And by electrochemical attraction, the chloride follows the sodium. So chloride Cl- is attracted to sodium Na+, and the two of them leave together. And now once the salt is leaving, then the water follows by osmosis. That's the big mechanism right here. We're able to reduce the fluid that was filtered here in the glomerulus to 1/3 of its original volume. That means if we start out at 180 liters per day, we're now down to 60 liters per day. While that is great, and certainly the proximal convoluted tubule is doing a great job, it's just not good enough. We can't afford losing 60 liters per day, and we'll see in a bit how we're going to reabsorb the rest of this. But here first, the significance of the proximal convoluted tubule reabsorption. So 2/3 of the sodium, chloride, and water are being reabsorbed across the proximal tubule into the vascular system. So here's 65%. 90% of the potassium is reabsorbed That reabsorption occurs constantly regardless of the hydration state, and it's not subject to any hormonal regulation. Interestingly, the expenditure at the proximal convoluted tubule is 6% of calories consumed at rest, and that is significant. That's what it costs you to reabsorb these 120 liters of fluids.